This video is about the NXP MCUXpresso software development kit. We'll show you a combination of two of the components of the middleware included. We'll use the Embedded Wizard graphical user interface and the Embedded Systems Academy CANopen and CANopen FD stack. Let's start by having a look at the demo. The demo consists of two boards. Here to the left we have the LPC55. And it has an accelerometer. So when we move it, the data is transferred to the i.MX board and visualized over there. The communication is done via CANopen. Next, we have a closer look at the components of this demonstrator. There are two boards, the LPC55 and the i.MX RT1064, both from NXP. The board on the left, the LPC55, has a regular DB9 CAN connector, and the board on the right has just the 3 pins for ground, CAN low and CAN high. I'll show you more details about the CAN cabling on the next slide. Looking at the code, the LPC55 code version can be used on multiple devices, also on some of the LPC55-4 family, whereas on the i.MX RT1064 side, you have to make sure you have a board with display. There are also versions available without the display, so make sure to get the one with the display. And the example code is for this exact board only. You cannot easily port it to a different one. Looking at the CAN cabling, on the left we have the J11, which has the 3 pins, 1 to 3. And here to the right we have the LPC55 with the regular DB9 connectors, and here the pins 2, 3 and 7 are used. Pin 3 of the jumper 11 goes to pin 2 of the DB9, that is the CAN low signal. Pin 1 of the J11 goes to pin 7 of the DB9, that's the CAN high signal. And we also need a common ground, that's the remaining pins. So pin 2 of J11 goes to pin 3 of DB9. In regards to termination, CAN always needs termination resistors at both ends of the network. On the LPC55 board, the termination is part of the board layout, and you just have to make sure it's enabled by setting jumpers 23 and 24. On the other board, we do not have termination integrated, so you need a termination resistor of about 120 ohms crossing between 1 and 3, so the CAN low and the CAN high. This is the i.MX board with the CAN connector installed. Looking at the software required, you of course need the MCUXpresso SDK. It contains the CANopen examples, and it has also pre-made alternate main files, and these contain the examples used in this demo. For the complete demo code, simply go to our webpage emsa.com/nxp. The latest version of the demo software will always be available there for download. In the following section, we'll have a look at where to download the software and how to flash it into the boards. On our webpage em-sa.com/nxp, we have our software for these two boards available for download, down here in the download section. We will not discuss the details of the SDK download here. Please see our other videos for that. The i.MX package is a zip file, and if you unpack it, you get a directory with the following content. There's a subdirectory with the flash CAN FD demo, and in there you'll find a batch file that you just execute to flash the program into the board. The entire flash process takes about 30 seconds to execute. I'll do a little bit of a fast forward here. And now to the LPC55 example, the slave version. this will just import into MCUXpresso. So let's start that. We'll just start a new space, demo space. To import, we go to Import Projects from File System, and it's not an archive anymore. I unpacked it, so I'll go to Desktop. There's my MCO. This is the directory we'll choose. And next, and we'll say copy project into workspace. Well, I'll keep them where they are, and I'll just take all the examples so they get all imported. And now you can see there's one called the Accelerator example, and this is the one we are interested in. From here we can build, flash and debug the software in the usual manner. Please see our other MCUXpresso videos for more details on how to do that. For those of you with an interest into the programming details, this section shows you how the existing demo program for the LPC55 is converted to the Accelerator demo. I have now MCUXpresso, the IDE, up and working here in my test space, my test workspace, and I loaded the LPC55 S16 software development kit, and the program examples I put into my project from the SDK are the I2C accelerometer value transfer example that reads data from the eval board. There's an accelerometer on there, so we get an X, Y, and Z value via I2C. This is the data I would like to add to the CANopen example. And on the CANopen example, we have the slave or device examples here. One, the MCO is the micro CANopen for classical CANopen, and the FD is the CANopen FD version. Let's look at the configuration files. Now in CANopen, we have the configuration files in the MCO config subsection. And here you can see the EDS and EDS-FD subdirectories. The EDS stands for the electronic data sheet. So that contains all the configuration of a CANopen device as it's communicated to other devices. And the electronic data sheet, EDS, we added by using the CANopen Architect Mini utility that we also provided for all users here of the MCUXpresso SDK and our CANopen middleware. So if you have that pre-installed, then just with a double click we can get that started and the file opens up. Let's have a look at the components of the electronic data sheet and the sections. There's a file section that's just about the file itself, but let's have a closer look at the device section. So here for the CANopen device, we have some generic information like the vendor name and a vendor ID. So if you later produce your own device, definitely replace the vendor ID and the vendor name with your own. And of course also specify your own product name and product code. When it comes to commissioning, this, if you already know that there will be a fixed node ID, then you can put this in here, otherwise leave it to 0. But for the file generation, we really need a node ID here, so that the CANopen node knows with which node ID to start. And here we also select the bit rates used. So we'll leave here the defaults, the nominal bit rate of 500 kilobits per second. And down here for CANopen FD, we also need to specify the data baud rate, and I'll leave that also at the 2 megabits per second. We'll have a look at the PDOs a bit later. Let's now look at the communication profile. Now, this is the 1000 hex area of the object dictionary, and we have things here like the device type. So that defines what type of device we are. Then we have an error register. somewhere down here we have a manufacturer device name, and we can see here's the default name for this, CANopen library NXP SDK, and we'll change this here to Excel example so that we can later see this is the accelerator example. Then there's a string for hardware and software version. We'll skip further down here to the 1018 record. This is also pretty important because this is the main identification object of your device. And here a total of 4 32-bit values. Again, the vendor ID, which is currently the one from NXP. So definitely that needs to be replaced when you produce your own device. We have a product code and a revision and serial number that we can place in here. However, the serial number can also be set during runtime. Before we go into the PDO parameters, we should double check the standardized device profile area, because here we have our regular digital and analog input and output lines. So we already said we'll use the read analog inputs for our XYZ, but maybe to emphasize what this really is, we can rename them here. Instead of using analog input 1, 2, 3, why don't we call them position 1, position Y, and this should be position X, and position Z. So these are the 3 X, Y, and Z. Then we set the read state and the write state. So write state is when we receive data from the network and we are writing it as output. Well, we said the first byte, we actually want to turn this into a command byte. And then the next step we'll do is we'll also add a new variable, something that is not part of the standardized device profile, and we do that in the manufacturer specific area. So here we'll say new entry, and we'll put this maybe at 2200. The hex 2000 area is all for manufacturer specific stuff, so number really doesn't matter here. And we'll call this our loop count. And I just want to count my how often the program counter runs through the main loop as a diagnostic output. So let's add this and make sure this is a read-only value of unsigned 32, and that we can also map it into a PDO. So with that, I think we have the process data set that we want to modify. And now let's look at the PDO configuration. Now for that we could of course go into the communication profile and go down here and edit all these manually. However, CANopen Architect really has a nice input feature here to simplify the input, and that is in the device section PDOs. Here we can now edit our PDOs. So in terms of data we receive, we'll set, you know what, on the receiving side we have a command byte. So let's see here at the end of the mapping, the contents will erase everything that's in here. And actually I should have only erased the end, but I can put this button back in here and say in the standardized device profile, the write output, the command byte is what I want to have. So we have a single entry mapped, it's the command byte, so only the command byte comes in. Then On receiving side, the second received PDO we don't need, so we can erase that. And on the transmit side, we'll use the tPDO1 to transmit our loop counter. So let's change here the content. I'll erase everything and place in here our counter, manufacturer specific, the loop counter. Okay. So we are transmitting here the loop counter. And in regards to the transmit PDO2, this is where we have our position X, Y, and Z. We'll erase everything behind it because we'll only say, oops, can I do? There you go. We'll only have the X, Y, and Z in here. So let's double check what else we can set in here. And for the transmit PDOs, we can also select an inhibit and an event time. The event time is a cyclic time, meaning that the PDO is transmitted cyclically with this time base. So we'll say, you know what, 1 second, 1000, is this in milliseconds, 1 second for the loop counter. We don't want to have that too often. And for the event, the position will for now leave the 500 milliseconds here as the event timer, but we'll now also look at the inhibit time. The inhibit time is, if that is set, then the devices also transmit their data not only based on the event timer, but also based on change of state. So whenever the data changes, the data gets transmitted. Now here for our loop counter, this would mean, hey, this, and also the accelerator, it changes constantly. There will be back-to-back transmissions over and over again. So with the inhibit time, we can add a delay and say, do not transmit this more often than every 10, 20 or whatever milliseconds. So for the loop counter, I would say let's not transmit this more often than 250 milliseconds. So I have to enter here 2500 because this is not in milliseconds, it's in multiple of 100 microseconds. And for the position value, we actually want to be pretty fast. So why don't we leave it here at the 20 milliseconds? So what the timer values here now do is that each of these transmit PDOs, so if we're looking at the position value here, it will be transmitted every 20 milliseconds if the data changes. If it does not change, then at least after 500 milliseconds, it will be transmitted again. So it opens up a communication time window where we say it will be transmitted at least every 500 milliseconds. So even if there's no change of data, we see some communication on the bus. However, if data changes, then it will be transmitted much faster, but never faster than 20 milliseconds. We are now ready to export our data. Maybe in between a save would be a good idea too. So if we do a right mouse click here on our project, we can do an export CANopen plus source code. So this exports the configuration files we need for CANopen. We can just double check where it goes. Yep, it goes straight into the EDSFD files. And we get a warning, do you really want to overwrite the old files? Yep, I want to overwrite. So files are generated, 0 warnings, source file export completed. Here we can also now generate the EDS file for it. We could also say export the EDS file and overwrite the previous one also. Yep, overwrite. Now let's go back to our IDE and see the generated files. So we have the entries and replies, the process image and the stack init. The entries and replies contains all the object dictionary definitions and separated by constant values. So here the SDO reply table is all the constant values returned. For example, our vendor ID, product code, and revision number that were hard-coded here. Then we have our generic entries, the G entries. These are longer than 4 bytes, so these are things like the manufacturer device name or a longer buffer here. And then the main table is just here, the OD entry. So this is always index, subindex, length, and if it's a read, write parameter or mappable to PDOs. And the first entries are here for our PDOs. So we have here the command byte, we have our loop counter, and we have our position X, Y, and Z. The process image.h, that is just the definition primarily of offsets, because down here for all the data we have laying in our process image, all data communicated is in one array, and so we have access to these via offsets, and these are defined here. So we can use later in our code to access the command byte. We can use this symbol here, the command byte. Then down here for the loop counter, we can use this symbol, and so on. And last, the stack init, that is simply doing some of the initializations, the CAN bitrate supported, and it has functions to init our PDOs, but also to init heartbeat consumers, if any, or emergency consumers. Next, let's look at main. Somewhere down here in sources, we have our main routine, and I'll make this a little bigger. Now let's look what the current example program is doing. All the way down here is the init hardware. Wait, where's my main? There you go. So you can see main just fits barely on the screen here, this low resolution. And all we do in main is really we init the hardware. Oops, there you go. So init the hardware. Then we have the reset communication. This is the MCO, micro CANopen user function, to initialize or reinitialize the stack, the CANopen stack. So that is done here. And then the main while one loop, it's really just an alternate call of process stack to work on the CANopen stack. And here the user process. So in this function, we do everything that your user code actually performs. And this is only called while we are in the network management state operational. So only when the device from a CANopen master is switched into operational do we actually start processing this user process. And down here is just a check for error, the bus off condition. That would be a serious CAN error. Then we would go to fatal error and initiate a reset there. Now looking at the given example here in user process, we have to definitely modify this to fit our new requirements. So I have something prepared that I'll copy over, and then we'll have a look at it. So let me now open step 1 of the file I prepared with the main with the new user process, and it started fairly simple. Now, just to show how the exchange between your application and the CANopen stack works, we'll use the two functions, read process data and write process data, to access data in the process image. So what I did here, I prepared my variables that contain actually the parameters that I want to communicate. So we have the command byte, we have the position values X, Y, Z, and we have the loop counter. These are static so that they are permanently in memory, not only here in a local function. And let's see how the communication works with the CANopen stack. So here we have the read process data. The address is the command byte, the length is 1, and this is the offset that we got from the process image file. So this is the offset into the process image. And so with this command, with this function, we take the offset, the process image offset, 1 byte, and copy it over here to the command byte. So after this function, the variable command byte has the latest value as received on the CANopen side. On the transmit side, to transmit data, we are taking here again the loop counter, the variables that we defined up here, a pointer to it, cast this all to 8-bit values. The length here is 4, here is 2, and again the offsets defined in process image. So with these functions, we simply copy these variables into the process image. So of course at this point we are not doing anything with these variables, it's really just updating them. So the stack now handles by itself if and when a transmit PDO is triggered for any of these. So if we change these frequently, then the change of state is triggered and the data will be transmitted by PDO. Our next step is taking data from the accelerometers example. That's why we have this all the way up here. So let's see how that is implemented. Well, we have here the sources. There's an I2C value transfer C file. Let's have a look at that. Make this big and get a brief understanding how this example works. Well, up here we have the prototype, so there are some functions to do all the I2C handling. And if we go down somewhere, there must be a main in here. There's read and write functions. These will just copy one-to-one over. Okay, there's a main. Obviously, there are some specific initializations for the I2C, so we need to create those too. And then after all the initialization, here it's a loop doing the reads. So this is the loop we can integrate also in our user process. And it really comes down to double check if the status value, if a read was completed from I2C, and if it was, then we can read the registers. And then here we have the XYZ. So that's straightforward. So let me copy this over too. So give me a second to copy over the file. Now we have in main. So I now merged into main coming from the accelerator example, the code. So in short, I had to copy all the definitions, prototypes, and variables used by this example. In the code section, I copied all the functions coming from there. And let me make this big again. And then further down here in, let's do the hardware configuration first. I also had to add the clocks from that example, the clock setup, and the I2C initialization is down here. So I added the I2C. It's really just merging from the other code, but now let's look at the essential part. This is in our user process. We now do the following. So in each call to the user process, we'll check the registers from I2C, and if new data is ready, actually that was a copy-paste error, this should be an if. So if the new data is ready, then we'll trigger the next read cycle, so that starts the next I2C read cycle, and from the buffer we can copy over our X, Y, and Z position values. So I think then all we need to do is build this. 0 errors, 0 warning. Let's do a debug. We are here. And for now, I'll just hit running, and then we'll have a look with CANopen Magic what the communication is on the network. Just a moment. Before we switch over to CANopen Magic, here down in the console window, we see the device fired up, and it did a reset communication, reset its bitrate, transmitted a boot up message and a pre-operational message. Let's now switch to CANopen Magic. This is an analysis tool for CANopen networks. And if we switch on our trace here, you can see the device spits out its heartbeat at a 1 second rate. Maybe we'll just give it another reset to restart. And you can see here, if I briefly hold the trace, yep, with the reset, there was a boot up, emergency cleared, and then the heartbeats come out. Now I'll switch the display here instead of sequence to fixed. This way each CAN message overwrites each other. And down here I can also do a read of the manufacturer device name that we changed earlier. So if I initiate a read for that, we can see here it's called the Accelerator example, as we modified it earlier. And for better data visualization, I defined here the X, Y, and Z parameters of the PDO that are coming. So if I now switch the node to operational, all nodes to operational, then we'll see there our PDOs are coming. So really the values for X, Y, and Z come out every 20 milliseconds. So that's the fastest possible that we configured. And also here the loop counter with 250 milliseconds. So this is the hexadecimal loop counter. Now let's look at the X, Y, and Z values. If I now start moving the board, they should change drastically. Yep, here you can see there's the flip over of the to FFFF here, also similar here. So if I just turn the board, it's not doing much here, really just waving it a little up and down, gentle motions. Now the board is now laying still. However, the input is really changing on the lowest bits all the time, because the accelerator values are really on a 16-bit level. On the lowest 1-2 bits are typically changing all the time. So depending on what you want to do with those in an application, you would need to filter those out and don't react to the lowest bit changes. Coming back to our main, I copied over another file. This is now the last modification I still wanted to make and show you how to react to the command byte. So I updated our user process, and here is where we read the current command byte. I added a copy of the last command byte value over here, and with that we do a comparison if that has changed. So if there is a new command byte coming in, then we check if it's 1, 2, or else, and in any of these cases we copy a new string to a 128 byte buffer. So depending on the command byte, the string at 2010 will be this, this, or this. So let's just build this and no errors, no warnings, and debug. And also just for now running, and let's have a look at the, so here's the boot up message. The device is in pre-operational, and if I read this 2010, then this is now segmented transfer. I'll stop here for a second. So here is the default text, and that was transferred in multiple packages, because 128 bytes is bigger than the biggest CAN message. Now, if I switch this back again to fixed, and we switch into operational, remember the command byte is only active when we are in operational, then I prepared here the corresponding PDO messages. So if we now transmit the message 203, so the command byte 1, so 203 was sent with data 1. If I now read this, we should see the other text. So read, yep, it says this is string 1. And if I transmit the 2, did I? Oh, yep, there's 2, 3. If I read it now, then it says 2. So that was just a quick modification to also show some correspondence to changing command bytes.